Okay. All right. So good afternoon, everyone. We are recording now. This is the last lecture, lecture number 50. Okay. And we just discussed the Tut-Birch formula that we saw yesterday. And we have proved one direction of it. Right. So observe that the less than equal to part is easy. We already discussed that. And this is the difficult part. Okay. So in particular, what we want to show today is that there exists a matching M and a set S of the vertices such that the cardinality of the matching is greater than equal to this quantity. Okay. And of course, if it is greater than equal to, then it necessarily implies that the two are equal because we already know it is less than equal. Okay. Implies equality. All right. So we are going to need a few ingredients in order to prove this. All right. So supposing you get such a matching and such a set where the thing holds with equality. Okay. So we will call such a set a barrier. A set S is a barrier if it satisfies this equation. If it satisfies this with equality with respect to some matching, which will necessarily be a maximum matching. Okay. So before we jump into the proof, we will need some concepts. And what I want to discuss is, what does a barrier look like with respect to a maximum matching? Okay. Or rather, what does a maximum matching look like with respect to a barrier? So let's see what I mean. So supposing you have a graph where you have a barrier. So let's say this is your set S, which is a barrier. And let's say M is your maximum matching. And let's say you get some odd components. So I'll draw 6 odd components for the sake of example, and 5 even components, which don't really matter. So because this is a maximum matching, and because this matching and the barrier satisfy this equation by definition of barrier, it means that the number of exposed vertices is exactly equal to the number of M exposed vertices is exactly equal to the number of odd components minus the cardinality of this set. So in this example, that will be 6 minus 4 equal to 2. Right? So with respect to this matching, you will have exactly 2 exposed vertices. So can anyone tell me, what will this matching look like? I'll ask you a very specific question. Could your matching have an edge like this? Is it possible for your matching to have this kind of an edge? There are only 2 exposed vertices. I claim that this cannot happen. Can anybody explain to me why this cannot happen? So you can't have this kind of edge in your matching M. Otherwise, you will run into some contradiction. No? No takers? All right. So I'll explain then. Notice that if you have this kind of edge in your matching, well, these are odd components. So if you want to match their vertices, at least one vertex has to go into the barrier for all of these odd components. But in that case, you are still left with three odd components, and that will give you three exposed vertices. But we know that the number of exposed vertices is exactly equal to 2, because in this example, we have 6 minus 4 equal to 2. Right? Does everybody follow this argument? So you can't have any such edges going from the barrier into any one component. In fact, in any maximum matching, what must happen is that exactly one of these vertices from the odd components, from some of the odd components, will match into the barrier, and your exposed vertices will come from the remaining two odd components. And that is how you get this equation. The number of exposed vertices is exactly the number of odd components minus the number of vertices in the set S. Okay. So this is an observation I want to capture. In any maximum matching M, each vertex in the barrier matches with some vertex in an odd component of G minus S. And in fact, all these components will be distinct. Each one will choose one odd component, and that is the only way you will be able to get this equality. And these components are distinct. Are there any questions or concerns at this point? This point is really crucial. We are going to use it in the proof towards the end. Okay, so that brings us to a concept. You see, all the vertices in the barrier, if you take any maximum matching, they will have to be matched. They cannot be exposed by a maximum matching. So that brings us to a distinction between the vertices. We are going to call some vertices essential and some vertices inessential. So the vertices in the barrier, they are all essential because they are matched by every maximum matching. And the vertices that are the other vertices may be inessential. Okay, so it's just a definition. Essential vertex is a vertex that is matched, or if you like, covered by every maximum matching. Otherwise, the vertex is called inessential. I'll give you examples. Observe that in an odd cycle, you can choose a maximum matching that misses any vertex. So every vertex is inessential. For every vertex, you can find a matching, which will be a maximum matching, that will leave that vertex unmatched or uncovered. So all vertices here are essential. Okay. Let's take one more example. Well, if you take I'll again take a very simple example. You can try more complex examples on your own.
Is this essential or inessential?
Sorry. Inessential. You are right. Thanks. I wrote something and I said something else. So right. So in the NOT cycle, all the vertices are inessential because you can find a maximum matching that leaves any vertex exposed. Okay. Whereas in an even cycle, or for that matter, in any graph with perfect matching, every perfect matching by definition has to match all the vertices. So all the vertices will be essential. Right? If you take any maximum matching, which will be perfect in this case, then all the vertices will be matched, so they are all essential. This is true for every perfect matching, right? By definition of perfect matching. Good. Maybe I'll give you one more quick example. You can do something like this. Yeah. Maybe let me make it a barrier. So this is going to be your barrier, and I can put one even component over here. And in this example, so the barrier vertices, notice that there is a matching that leaves exactly two vertices exposed. You can choose any two vertices, like these two, for example, here, and you will be able to find a maximum matching that matches all the other vertices, except for those two that I have drawn in a box. Okay. In particular, this set S is a barrier, and all of its vertices are going to be essential because they have to be matched by any maximum matching, as we just discussed over here. Right? However, for all the other vertices in this graph, wait a second. Right. And in fact, right. So in this graph, you can check later that all the odd component vertices are actually inessential, and all the remaining vertices are essential. So these black colored vertices, you can check that they are all essential. However, the other vertices, which are white colored, they are inessential. Okay, so these are essential and these are inessential in this last example. Okay, and the observation I want to make is that if S is a barrier of a graph G, then each vertex of S is essential. However, there may also be other essential vertices. Okay, so this is an observation. Are there any questions or concerns regarding this observation? Okay, if not, I want to state one other way of thinking about essential and inessential vertices real quick. So observe that if G is any graph and V is any vertex of the graph, let me introduce a notation. So when I say M of G, I mean some maximum matching of G. I will not generally use this notation. What I will use is cardinality of M of G. Okay, so now there is no ambiguity. This means the size of a maximum matching. So this is cardinality of maximum matching of G. Okay, so we'll find this notation a bit useful. So the observation I want to make is the following. Consider any vertex of the graph. what happens if you delete this vertex? So I want to relate the cardinality of a maximum matching in G minus V with the cardinality of a maximum matching in G. Can someone tell me how are these two related? Can they be very different from each other? Is it possible that the maximum matching in G has size 8 and the maximum matching in G minus V has size 6? Is that possible? Can you go from 8 to 6 by deleting a vertex? You're deleting just one vertex. Can you change the size of a maximum matching by 2?
No.
No, right? So what is the maximum you can change it by?
1.
1. Exactly. So in other words, this quantity is either the cardinality of maximum matching in G or it is this minus 1. Okay? And observe that a vertex V is essential if and only if it goes down by 1. Okay? And if it remains the same, then that is an inessential vertex. Okay? So that's another way to think about an essential vertex or an inessential vertex. All right? We'll find both of these viewpoints useful. Okay? All right. So are there any questions or concerns at this point? Maybe I'll write this as essential because all right. So we are going to use all these concepts. And now let's start with a proof of the theorem. We will get stuck somewhere, so we will see how to deal with that later. Okay, so the proof is by induction on the number of edges of the graph. Okay, and let's first assume or consider a base case, which is when there are no edges in the graph. Okay, if there are no edges in the graph, then the size of the maximum matching is exactly 0 because it is the empty set, right? And consider S to be the empty set. So the number of odd components minus the set S, well, if there are no edges, every component is an odd component, right? And we are not deleting anything, so we will get exactly the number of vertices of the graph. Every vertex is an odd component. Okay, so this is exactly the number of vertices, right? And now observe that the right hand side, number of vertices minus the odd components plus cardinality of S divided by 2 is exactly 0. Right? So the statement holds. Right? So we choose the set S to be the empty set and everything works out. All right? So that's the case. That's going to be our base case. I generally don't write this explicitly, but in case you are used to it, it might be useful. And now let's consider our induction step. So now let us suppose that the graph has some edges. And let VW be any edge of the graph G. All right. So we are going to consider two cases. So right, we are looking at some edge VW. So in one case, we will consider that one of these two vertices is um, an essential vertex. Okay, and that will be the easy case of our proof. So case one of V and W is essential. Okay, it doesn't matter. So adjust notation such that V is essential. Okay, so what does it mean for V to be essential? It means that the cardinality of this maximum matching in G minus V will go down by 1. Yeah. Well, we have deleted the vertex V. Therefore, we have deleted the edge VW. So the number of edges has also gone down when I delete that vertex, right? So by the induction hypothesis, I know that the G minus V graph will satisfy the induction hypothesis, right? Will satisfy our desired conclusion. By induction hypothesis, G minus V has a set S, which is a maybe let's call it T. Let's call it set T, which is a subset of the vertex set of G minus V, such that this equation holds. Okay, so the cardinality of the maximum matching in G minus V is exactly equal to the number of vertices in G minus V minus the odd components in G minus V minus T plus the cardinality of T, whole thing divided by 2. Okay, well, but that means that the cardinality of the maximum matching in G is this quantity plus 1, right? By using this equation. So that means that we have I'm going to add 1 to this. It's this plus 1. I'm taking it to the other side. And so that's as good as adding plus 2 because I have a divided by 2, right? Are there any questions or concerns at this point? We have just done some basic manipulations, right? Okay. So now can somebody tell me what should be my set S? So I want to write everything in terms of a set S, right? So that the equation that we want to prove holds in the graph G. So what should the set S be? So T is a barrier in G minus V. I claim that from this barrier in the graph G minus V, we can construct a barrier in the original graph G. Does anybody see how we would do that? Well, if you look at these quantities here, right, things start becoming a bit clear. What we want is a set S, and we want to get rid of this plus 2. So one way to do that would be to simply take T union V. Okay, if I do that, then cardinality of S is exactly equal to cardinality of T plus 1. So that is how I can take care of one of the extra ones I have here. And the number of vertices in the graph G is also one more than the number of vertices in the graph G minus V. So in fact, if I do this, I get exactly the number of vertices in the graph G. So one of these plus ones is absorbed here. Notice that the number of odd components, if I delete the vertex V and then I delete the set T, it is the same as deleting the entire set S. right? So this is exactly this quantity. And the set T plus 1 is exactly the cardinality of the set S, right? But that's it. That's exactly what we want to prove. We wanted to prove that there is a matching M in the graph G and a set S that satisfies this equation, right? And we got this set T in the smaller graph. And then using the fact that the vertex is essential, we were able to convert that barrier T in the smaller graph into a barrier in the bigger graph. Okay? So we are crucially using the fact that the vertex is essential. Otherwise, you would not have been able to do all these manipulations. The problem is, what happens if neither of these two vertices is essential? Okay? So that's the, are there any questions or concerns regarding this case? So if this situation does not happen, that means that for the edge you have picked, both the vertices are inessential. And that is the case we need to deal with. Case 2 is that both V and W are inessential. Okay? Notice that this is a theorem that holds for all graphs. Right? And you expect this to be somehow different from the bipartite stuff, right? Because otherwise, why can't we just use the same arguments that work in the bipartite case, right? In particular, why doesn't the Koenig-Egervari theorem hold for all graphs? So you expect somewhere to see odd cycles. Everywhere in non-bipartite matching, we had these blossoms, which were nothing but odd cycles that we shrunk into single vertices. Turns out the same idea is going to rescue us here. We are going to find an odd cycle. We need a lemma for that. I will state that later. We will find an odd cycle. We will shrink it to a single vertex, similar to blossom shrinking. And we will use induction on the smaller graph and go back to the bigger graph to prove the statement we want to prove. Okay, so that is actually what we are going to do. Let me state a lemma. So this is lemma 5.5 that we still need to prove. So G is any graph and VW is any edge of the graph such that V and W are both inessential. In this case, we will prove that there is an odd cycle in the graph. Then G has an odd cycle Q containing the edge VW, containing edge VW, such that on top of this, we want the following to be true. When we shrink this odd cycle to a single vertex little q, maybe I want some, such that let us call this graph G prime. G prime is G shrink vertices of Q to a single vertex little q. What I want is that the small vertex Q, little q, is inessential in the smaller graph. Okay, so I have found an odd cycle. This is in the graph G, and I shrink this to a single vertex Q, as we did in the blossom shrinking. And this is the graph G prime. And the claim is that this vertex should be inessential in the resulting graph. Okay, so for now, let us assume this lemma and prove the theorem, and then we will come and prove this lemma. Are there any questions regarding the lemma statement? Okay. If not, let us move to proving our theorem. So by lemma 5.5, there exists an odd cycle Q in the graph G such that the vertex okay, so containing this edge VW such that the little q vertex is inessential in the graph G prime, where I shrink q to a single vertex little q. Okay, good. So we'll use this odd cycle, right? So we get this odd cycle and we go to the smaller graph. All right. Now, because the smaller graph, we have shrunken a whole odd cycle. So all the edges of the cycle have disappeared. In particular, the number of edges has gone down. So by the induction hypothesis, this smaller graph is going to contain a barrier, right? That's how induction works. Every time you get a smaller graph, where smaller here means less number of edges, you know that the statement you want to prove holds, right? So by the induction hypothesis, there exists a barrier, let's call it S only, in G prime. Okay, what does that mean? I.e., okay, so here I want to make a small break. Yeah. Okay, let me do it in this way. So what does it mean to be a barrier? It means that the size of the maximum matching in G prime is exactly equal to the following quantity, the number of vertices in G prime minus the number of odd components in G prime minus S plus the cardinality of this set S divided by 2. Okay. But rather than working with the size of the matching, it's going to be slightly easier in this case to work with the number of exposed vertices. Remember, the size of the matching and the number of exposed vertices are related by this equation, right? So I will, instead of working with the size of the matching, I will go to the number of exposed vertices. Okay, it's just going to be a bit easier to think about that rather than doing lots of big manipulations. So, which is the same as saying that the number of exposed vertices in G prime is exactly this quantity where I have to flip the second sign, right? So it's exactly equal to the number of odd components. Okay, where the number of exposed vertices is given by capital U of G prime. Number of M G prime exposed vertices. Okay. Are there any questions or concerns at this point? Is it clear what we have done so far? We have gotten a smaller graph G prime. By the induction hypothesis, we know that in the smaller graph, there is a barrier. Let us call it S. Barrier means it satisfies this equation, right? But that is the same as satisfying the second equation, which is in terms of the number of exposed vertices, which will be easier to think about in this case. All right. So now I want to prove to you that the number of exposed vertices in the original graph is also the same quantity, where I need to replace G prime by G, of course, because we are going back to the original graph. Okay, so let's make a drawing. So what does the drawing look like? We are looking at a smaller graph G prime, and we have some barrier over there, S. We have some odd components, and we have some even components. and we have a vertex little q. Can remember this little q vertex is inessential as per this lemma statement. We haven't proved the lemma yet. We are using the lemma without proof right now. So this little q vertex is inessential in this graph G prime. So where can this little q vertex be? Can it be in the barrier? Or have we made an observation that does not allow that? So where is little q? I claim that it cannot be in the barrier. Can anybody see why it cannot be in the barrier?
All vertices in barrier is essential.
Exactly. We have made an observation over here. All the vertices of a barrier have to be essential, right? That we already know. So because of the lemma statement, this vertex little q is inessential, so it can't be in the barrier. So there are only two choices. Either it is in one of the odd components or it is in one of the even components. Well, it doesn't matter. No matter which component it is in, I can blow it up back to the original vertices of Q. And this set S, the graph will still have the same structure. That supposing Q is in an odd component, what will happen is one vertex will now be replaced by 5 or 7 vertices. So this will still be an odd component in G minus S. Okay? And if it is an even component, then the component will still be an even component in G minus S. So since Q is inessential, Q does not belong to the barrier. Note that Q is in some component. Well, it implies that Q is in some component of G prime minus S. And the component has the same parity. What I mean is I'm using words slightly sparingly. What I mean is that the number of vertices in that component, if it was odd, it will remain odd. If it was even, it will remain even. It has the same component, and the component has the same parity in G minus S. Okay. In particular, the number of odd components and the number of even components in G minus S will be the same as G prime minus S. Okay. So in particular, this implies that the number of odd components in G minus S minus the cardinality of S is equal to the number of odd components in G prime minus S minus the cardinality of S. Okay. This is key. Oh, but I have the number of exposed vertices in G prime. That's not a problem. Remember, when we discussed shrinking an odd cycle, we noted that if we have a matching which leaves some number of exposed vertices after shrinking an odd cycle, we can blow up the odd cycle and we will be able to extend the matching on the odd cycle, and the number of exposed vertices will remain the same. We call this proposition 5.4 when we were discussing the Blossom algorithms, right? So the number of exposed vertices in G and in G prime is the same because we have simply shrunken a blossom or an odd cycle, right? So here we are going to use this. Recall proposition 5.4, which says that the number of exposed vertices in G is the same as the number of exposed vertices in G prime with respect to maximum matching, right? So here we are looking at number of M exposed vertices. Maybe let's just say number of exposed vertices with respect to some maximum matching of G prime. And here we are looking at the same quantity, with respect to some maximum matching of G. This is the reason our maximum matching algorithm or our perfect matching algorithm worked, right? Okay, but that's it. That means that the number of exposed vertices in G is exactly equal to this quantity by putting these two equations together. Right? So this implies that the total number of exposed vertices in G is precisely this quantity. And that is exactly what we want to prove, because we noted that this is same as saying that the size of the maximum matching is equal to this quantity, right? So sometimes it just is easier to think about the exposed vertices. So this is the same as saying that the size of a maximum matching in G is precisely the number of vertices of G minus the odd components of G minus S plus the cardinality of S divided by 2. And that proves the Tut-Birch formula, modulo lemma 5.5. Okay, so I'm going to go up to 6 p.m. I think by 6 p.m. we should be able to complete the proof of lemma 5.5. But before we go on, are there any questions? Yeah, go ahead.
If both U and W are essential, we need to deal with that case also, right?
No, so the first case was, oh, wait a
One
second.
of them is
One of them is essential. No. So when I say one of them, I mean at least one of them. Sorry.
At least, okay.
Yes. Whatever we did not rely on W, right? So in fact, the only thing we used was that the vertex V is essential. So if at least one of them is essential, then we are in case 1. Otherwise, both of them are inessential, and then we are in case 2. Yeah?
Oh, okay.
Yeah. Good. All right. So are there any questions or concerns regarding the proof? If you haven't seen inductive proofs in graph theory for a long time, this might be a bit of what's going on moment, but go through it again. It's not a proof that you see the first time and you totally get it, right? I mean, I've seen it many times, so it's a different story. But yeah, there are a lot of different ideas being used, and it is a non-trivial inductive proof actually. Yeah. All right. So if there are no questions, then the main thing that we are using is lemma 5.5. And you might be thinking, this is something about matchings. Where is the symmetric difference of two matchings? Every time you deal with matchings in graph theory, you always look at symmetric difference of two matchings. Turns out we will use it in lemma 5.5. Okay. So just go through the statement, right? We have a graph G, and we have these two vertices that are both inessential, and there is an edge joining them. We want to prove that there is an odd cycle containing this edge. And then we want to show that the small vertex Q is inessential in the graph after shrinking this odd cycle. Okay, so let's quickly prove this lemma. All right, so what are the hypotheses? G is our graph, and VW is an edge, and V and W are both inessential vertices, which means that there is a maximum matching that misses each of them. Okay, so what we will do is we will take a maximum matching missing the vertex V, so it will not match the vertex V, and we will take a maximum matching missing the vertex W. Okay, so it's going to be a slightly strange notation, but it makes sense in some sense. So MV is a maximum matching of G such that the vertex V is not matched, is M exposed. Sorry, MV exposed. Okay. And MW is going to be a maximum matching of the graph G such that W is MW exposed. Okay. Let's make a drawing with some colors. All right. So let's say the red colored matching is MV, and let's say the blue colored matching is MW. Or let me actually use green, it might be more visible. Okay, so we have a red matching and a green matching. All right, and we have this edge VW in the graph. So the red matching, it does not match the vertex V. So what I will do is I will put a red circle around V, indicating that it is not matched by the red colored matching. Okay. However, observe that vertex W has to be matched by the red colored matching, because otherwise you could add the edge VW and get a bigger matching. So because V is MV exposed, W has to be matched by this matching somewhere. And by a symmetric argument, this is MW exposed, and this vertex has to be matched by some edge in MW. So this is an edge of MW, and this is an edge of MV. Okay, we've got two matchings. When you have two matchings, what you do is you look at their symmetric difference, or you look at their union. It's the same thing really. It's not really, I mean, it's not the same thing, but you can think of either of them and come to the same arguments. Okay. So now let us look at the symmetric difference of these two matchings. Consider MV symmetric difference MW. What does it look like? Let us look at the component containing the vertex V. Let P, observe that the symmetric difference of two matchings is always a bunch of paths and cycles. Hopefully we have discussed this before, or you have seen it in another course. In this case, the only way you can get a cycle is if all the vertices are matched, in which case you will have a red-green alternating cycle. However, here you have exposed vertices, so it won't be a cycle. The component containing the vertex V will not be a cycle, right? Because there is no red colored edge at the vertex V. So let P denote the component. Maybe let me leave some space. Let P denote the component of this graph. So what is this graph? We are taking all the vertices, but we are taking only the edges which are red or green, but not both, right? Containing vertex V. So what does this component look like? Well, it's a red-green component. So you could have a red edge, you could have a green edge. It will have to stop somewhere. It is going to be a path, and it will stop at some exposed vertex. Okay. Supposing it stops at some vertex Z, which is not W. Let's say Z is not equal to W. If this vertex, so this vertex has to be either MV exposed or it has to be MW exposed. The case I have drawn right now is when it is MV exposed, which means there is no red colored edge incident here. But then there is a contradiction. Does anybody see the contradiction? I claim that this cannot happen. I claim that you cannot have this kind of situation where the path starts
This
at
is an augmenting path.
This is an augmenting path, exactly. This is an augmenting path for the red colored matching. So you will get a bigger matching, but it was a maximum matching, so you can't have this situation, right? So we can't end with an MW edge at a vertex Z which is not W. Okay. What about ending at a red colored edge? Supposing I end at a red colored edge. Well, that means that the vertex over there, it's exposed with respect to the green colored matching. And let us suppose that this vertex Z is once again not equal to W. Do you see a contradiction again? I claim that there is a contradiction once again.
Contradict MW is maximum matching.
Exactly, exactly. So you take this path, and you take this edge, and now you have an augmenting path with respect to the green colored matching, which is also a problem because the green one is also maximum matching. So both of these situations lead to a contradiction. So the only thing that can happen is that this path ends at the vertex W. Okay, that's great. So we go like this, and eventually we go back to the vertex W. Ah, this is good. Can somebody tell me why this is good? We have proved part of the statement.
We got an odd cycle.
We got an odd cycle. The path P plus the edge VW is our odd cycle. Right, so this is the path P and this is our edge VW. Okay, so that is the argument. So observe that P must end at vertex W. Otherwise, we get either an MV augmenting path or an MW augmenting path, both of which lead us to a contradiction. And now the path P plus the edge VW is our desired odd cycle. In the graph G containing the edge VW, right? We wanted an odd cycle containing this edge. So we got an odd cycle containing this edge. Okay, we need to prove one last thing. We need to show that in the smaller graph, after shrinking this odd cycle, the shrunken vertex little q is an essential. That's not too difficult actually. Let me just convince you. So this is a graph G, and the graph G prime is when we shrink this entire cycle into a single vertex little q. Okay, let me just draw one of the two matchings outside. So observe that the red colored matching will look like this, because in the odd cycle, all the vertices are already matched except for one vertex, which is an exposed vertex. Okay, so if you shrink this odd cycle, you will still be left with the same kind of matching outside. If there was a bigger matching in this graph, in the graph G prime, then you would be able to go back to the original graph and get a bigger matching in the original graph by taking the edges from the odd cycle. Okay, so this is a simple observation. If there is a bigger matching in G prime, then we can simply blow up the cycle and we can again increase the size of this matching by as many edges that are used in the original matching, in the red colored matching, right? So that means we'll get a bigger matching in G, but both the red colored and the green colored ones were maximum matchings in the original graph. Okay, so that's just a small part. So observe that if G prime has a bigger matching, then let's say MV minus the edges of the cycle, then G has a matching bigger than MV itself. But that is a contradiction because MV was a maximum matching. Of course, I could have done the same thing with NW. Okay, so which means that this matching here, the MV minus the edges of the cycle is a maximum matching, and it misses the vertex Q. Q is exposed. Therefore, Q is inessential by definition. There is a maximum matching in G prime that leaves the little q as an exposed vertex. So by definition, Q is inessential in G prime. So in particular, Q is inessential in G prime since Q is M prime exposed, where M prime is the original red colored matching minus the edges of the odd cycle. Okay. So that's it. We have proved the lemma and we use the lemma to prove the theorem, and that completes the proof of the Tet-Birch formula. And that is the final result of this course. Sorry, it was a bit fast. I should have planned it a bit earlier, but maybe go through the lecture again, and hopefully everything has been covered. So if you go through it again, hopefully everything will be clarified. But if there are any questions or concerns, I'm here for another 10 minutes or whatever. In fact, I'll stop recording in case you want to ask me anything else unrelated to the course or whatever. Yeah. So thanks a lot. I'm going to stop recording now.